everyone, here we are at Sibiu Innovation Days. I have next to me Alex. Hi Alex.
Hi Daniel, nice being here.
Alex is an engineer in NXP Romania, and he came and had a lecture yesterday. He explained how you can deploy neural networks on mobile devices and why is this a thing, right?
Yeah, I tried yesterday, but we had a couple of minutes. I need an entire course.
It's never long enough,
yeah,
right?
Exactly.
To show that. But you still explain. So why don't we go there? We have the cloud, which is powerful, right? And cloud has the computing power and the muscles, and we know what cloud can do, right? And we can train neural networks there and do all kind of these AI algorithms. But then we have the edge devices, right? These are all the devices that we have, you know, in our daily lives, right? Starting from smartphones, smart watches, There are some benefits of having algorithms running on these edge devices rather than in the cloud. What would that be? You know, the incentive to run there.
Yeah, of course there are benefits, and the most important one, or the first one, it's the latency. Imagine that you have to enter your house. At the door you
have a smart lock, right? And you want that smart lock to open when you come at home, right?
Exactly. Maybe it's a fingerprint or something like that. You don't want to put your finger there and
wait until it goes to the cloud, it comes back from the cloud, and now it's not you. All right, no, so you don't want that, right?
Exactly, and in that case, we do that authentication on the device. We use some algorithm that detect that, yeah, you are Daniel, you can enter, and you don't let me in your house.
So these are the benefits, right? But deploying on edge devices is presenting some challenges, because edge devices, comparing to the cloud, have limited compute power. They should be low power in consumption, right? And usually they come up with limited memory. How do we deploy the network there? What is the trick?
Yeah, we have a couple of techniques to make this network smaller, so we don't have to deal with the huge and complex networks. And that's what we discussed about yesterday, a couple of these techniques, and detailed a bit one of them, which was the quantization topic.
So when you have a neural network, that is roughly, let's do a crash course on neural networks. So we're going to explain you in 20 seconds. As a structure, a neural network has an input layer and an output layer. And in between, there are some hidden layers. It depends on the way the network is designed, on how many layers and how many nodes one decides to have. All these neurons and all these lines represent data that is consumed and is having a value and it's having a meaning in this algorithm to output the data. Fundamentally, a neural network is a function with a lot of parameters. During the trainings, these parameters are fine-tuned, and during the consumption of this function, during the inference phase, these parameters are used to come up with the right result. Now, the problem is that these parameters are usually floating point values on 4 bytes to have the accuracy to be well represented. They take a lot of memory because there are a lot of values, and they also ask a lot of computing power because calculations with floating points are quite intensive. Now, how can we shrink this network? How can we deploy this network on an edge device which has a limited memory and a limited compute power?
We have the option to optimize a bit the model. And how we do that? We have a couple of techniques. One, and the most obvious, would be that when we design the neural network, to add fewer layers, right when we design the network. But then are some techniques specific to, or more advanced to the neural network, like the quantization topic, which I detailed a bit more yesterday. So the quantization topic, it's the fact that we make the network a bit smaller, and that helps us to feed that into the memory of the edge devices, which has the limited memory. And as well on the compute side, we make it faster for the inference.
Secret is how you optimize but not lose the performance, right? So this is what you were spending time explaining yesterday.
Yeah, exactly. We have to find the trade-off between the accuracy and the memory. And For the quantization, as you said, we can quantize to different target precisions. And for the inference part, we win as well on the memory that we can fit into the memory, but also in an embedded device, we have the memory and the compute units. And having the network smaller, it helps when we bring the weights from the neural network in the compute units. We need less memory bandwidth for that fact. Right. And as well, on the compute side, doing the operations in integer, it's faster than doing the floating point operation and more efficient on the energy side.
All right. And how much of the performance do you lose, right?
Yeah. So usually if the training it's trained well and it's able to generalize on our data set, the performance should be, for the larger network, the accuracy loss should be in the range of 2-3%. We consider that acceptable. And you ask about the techniques. There are two main techniques. Okay. One is the post-training quantization. The network, it's already trained. We usually find pre-trained networks by the open source community or from the research, and we take those pre-trained and try to quantize them. In that case, we lose a bit more precision in the post-training quantization, and there is the quantization-aware training. This one, we train right from the beginning, the network with the quantization in mind, and that helps us a bit preserve the accuracy better when we do the actual quantization.
So basically, on this second method, when you pre-train with quantization in mind, what you actually do, you decide which layers will be maybe integers. You can preserve some layers to be still floating point to have some accuracy, right? So you do kind of a mix of where exactly and how you optimize, right? And if you find the right mix, then the deterioration is marginal. Right?
Yeah, that's another trick, and it's a good one that helps us to find a better trade-off in between the accuracy and the memory. With the mixed precision quantization, that's how we call it. Okay. In the neural network, we have the layers, and each of these layers has a different numbers of parameters. And what we can do with this mixed precision is that in the layers with fewer parameters, they have fewer parameters, so they consume less memory. We can keep those layers in higher accuracy, even in the floating point precision, and the layers which are larger have more parameters and consume more memory. We can be more aggressive with those layers and quantize it to int 8, int 4, or whatever we think.
Because there are so many dependencies on how you can achieve the best performance, it's clearly that a customer, an NXP customer trying to move these neural networks on NXP processors and on application and use cases with NXP processors needs some guidance, right? Exactly. Needs some help to find the right mix, to find the best recipe and so on. And this is what your team is actually doing, right? You're working on products and solutions that are ultimately going to guide NXP customers on how to do this quantization, pruning, and design of the network altogether from the beginning in a smart way that it fits on the processor, right? This is what you work on.
Exactly. We provide tools and runtime libraries, those which are running on the actual platform, and we implement different optimization techniques of the neural network on the tools side. And the key with all of them is to find the right balance between them, so you can meet your accuracy, your latency, and the memory requirements for your application and for the device. We implement different methods in the tools, and we have the runtime libraries which leverage the accelerators and the compute units we have on our devices.
Yeah, because this is another secret, right? You can run on the main core all these things, of course, but in some cases, depending on the processor, you might have a dedicated accelerator for machine learning, and then you can move the code and run that actually on the accelerator, so the performance is even better, right? And you guide, and we guide our customers in general on how to do that and help them along the way.
Exactly, that's what we do. We provide those accelerated implementations.
Yeah. So yesterday we got a lot of questions from students like, what are you doing? What is R&D in Romania doing? What is NXP and R&D meaning? Now you have a real example, right? So this is the kind of work. It's not the only thing, right? We do way many other things, but this is the kind of work we do in NXP and in Romania, right? Thank you very much, Alex, for your time. It was a pleasure talking to you. Definitely, I learned a lot. So I let you see the presentation. You can check it also online. I think even the original one. And yeah, good luck there. It was really fun.
Thank you for having me. I can't wait to be back here in Sibiu.
Yeah, Sibiu is nice, and I hope they will do more and more events like that.